This is Probability Notes 2, Addition Counting Principles. Today we're going to talk about probabilities or number of outcomes in a dice rolling event. We're going to calculate intersections and unions, and we're going to also work with Venn diagrams. First, I want to go back to dice rolling, which we talked about the other day in class. We're going to let A be the event of rolling a sum of 7 with 2 dice. And this notation, P of A, again means the probability of rolling a sum of 7. You might recall that these different sums always appear along diagonals on your dice rolling diagram, and the 7 is no exception. The 7s occur basically all along this diagonal right here. There are 6 different events or different ways of rolling this sum. And our sample space when working with 2 dice was 36. There were 36 different outcomes represented by the numbers inside these little squares here. Obviously, the probability of not rolling a sum of 7 is what's left over. It's these other blank squares. Now you could add these individual numbers together, all the 2s, 3s, 4s, 5s, 6s, 8s, 9s, 10s, 11s, and 12s. Or what you can do is you can always take this number away from 1. Not rolling means everything but this. So you could take 1 minus 6 over 36. You might recall that's the same as 36 over 36 minus 6 over 36. And this is equal to 30 over 36. In both of these cases, you can reduce your answers down. If you want to reduce 6 over 36 to 1 over 6, that would be appropriate to do so. And if you want to reduce 30 over 36 to 5/6, you can do that as well. N of A refers to the number of ways of rolling a sum of 7. We said there were 6 ways altogether, and it's basically the numerator of your unreduced fraction. We're now going to calculate intersections. This little upside down U symbol is an abbreviation for the word intersect. It's also a synonym for the word and. So whenever you see this upside down U, you can replace it with the word intersect or the word and. Here's a scenario where we're going to let A be the event of the first die rolled showing a 4, and B is the second die as a multiple of 2. Find the probability of A intersect B, which can be also read, find the probability of A and B. If we go to our chart, the first die showing a 4 is any number that's in this row right here. I'm going to circle the values in this row with my blue pen. The second event is B, which is the second die as a multiple of 2. So I'm going to circle anything that appears in the 2, 4, or 6 rows, because that would be where the second die is a multiple of 2. I'll use a different color for this so it stands out a little bit better. Now what we're looking for is the probability of A and B. We're looking for places where the first die is a 4 and the second die is a multiple of 2. And that happens anywhere where the blue and red rings intersect. And you'll notice that specifically this happens in 3 places. Right here, here, and here. These are places where the first die is a 4 and the second die is a multiple of 2. This happens where the blue and red intersect. These 3 locations are our event. Our sample space is 36. Our answer is 3 over 36, which you can reduce to 1 over 12. See if you can solve the next 2 problems. Pause your screen, and then we'll come back in just a moment and we'll answer the next 2 questions. Okay, so let's go back to event A here. A in the second case is the first die is a multiple of 3. I'm going to circle our 3 and 6 die values that go across this row in blue. For event B, it's the event that the sum of the dice is 7. Now the sum goes along the diagonal again. That would be these values that go along here. We're looking for places where the first die is a multiple of 3 and the sum of the dice is 7. This happens in 2 locations. It's also where the blue and red intersect. So I'm going to circle those 2 locations here by rolling a 3 and a 4, and here, rolling a 6 and a 1. So we use the term and. Notice here it says n, so I want the number of places where the first die is a multiple of 3 and the sum of the dice is 7. So we're going to write 2, but not over 36 because it's not a probability problem. It's an n problem, so we just want the number of places this occurs. For the third example, let A be the first die is larger than 4, B is the sum of the dice is 3. Again, I'm going to go to my blue pen, And I'm going to circle places where the first die is larger than 4. Larger than 4 means, well, it's got to be 5 or 6. So any numbers in these bottom 2 rows represent our first event. B is the sum of the dice is 3. So we're going to look for where the sum of the dice is 3. Again, that's going to go along our diagonal. Just these 2 locations. So where's the first die larger than 4 and the sum of the dice is 3? Well, that can't happen. If you roll a first die bigger than 4, your sum's already going to be bigger than 4. It can't be 3. There's nowhere that this happens. You'll notice the red and the blue do not intersect anywhere. So our answer is, well, nowhere. There's no intersection. These don't intersect anywhere. They have nothing in common. So we say our answer is 0 out of 36. If you just want to put 0, that's equivalent, and that's fine. If this probability is equal to 0, we say that A and B are mutually exclusive events. They each exclude each other. A and B have no events in common. We're next going to calculate unions. The abbreviation U means union. It has a synonym for OR. So we have some formulas for calculating unions. One is this: the probability of A union B, or A or B, equals the probability of A plus the probability of B minus the probability of A and B. There's a similar formula for the number. Basically, everything is the same except we're going to replace the P's with N's. Let's look at this event where we have A is the first die showing a 4, B is the second die as a multiple of 2. We just worked with these examples earlier. I'm going to circle the event A, the probability that the first die is 4 in my blue pen, and I'm going to choose my other pen. For B, the second die is a multiple of 2. That would be these 3 columns of data here. Now, to calculate the probability of A union B, or A or B, we're going to look at 3 values here. We're going to look at the probability of A, the probability of B, and the probability of A and B. Now, we've already kind of talked about the probability of all of these values. The probability of A is basically what you see in blue here. There are 6 different ways that you could get a first die showing a 4. And I'm not going to reduce that. I'm just going to leave it as 6 over 36. The second event is the second die is a multiple of 2. There were 6, 12, 18 different ways that this could happen. Half of our diagram. Now you could write as 1/2, but we're going to leave it with the same denominator. The probability of A and B were these 3 different intersection points. Remember, A means intersection. So it was these 3 values here make up the intersection. And when you add these values together, 6 plus 18 is 24, minus 3 is 21. You're allowed to add them because they all have the same denominator. We tried to keep them as common denominators. And you get 21 over 36. You are allowed to reduce this down to 7 over 12. So what does our answer 21 over 36 mean? It means there are 21 out of 36 different ways where the first die could show a 4, or the second die could be a multiple of 2. Or in math means either the first event or the second one, or both. And if you were to count anything that is circled here, make sure you're only counting everything once, you would count 21 different things. One easy way to look at it is you have 6 down this row, 6 here, that's 18, 19, 20, 21. We're not double counting the 6, 8, and 10. That's the reason we subtract off this 3 here. If we just added 6 plus 18, this 6, the 8, and the 10 would have been counted twice. So we don't want to double count those numbers. That's why we subtract them off. See if you can use these formulas correctly in answering these next 2 problems. Pause your screen and we'll come back in just a moment. Let A equal the first die as a multiple of 3. We've already done the multiples of 3 already. That would be these numbers in this row here and the numbers in the other row down here. Working with a sum of 7 is again our diagonal, and what we're looking for is the number of ways that events A or B could occur. To calculate this, we're not working with probabilities, so we have no fractions here. We're just going to take the number of ways that the first die is a multiple of 3, the number of ways that the sum of the dice is 7, and we're going to subtract off any numbers that get double counted. So for event A, there were 12 different ways that were circled in blue. For event B, there were 6 different ways circled in red, and there were 2 ways that got circled twice. We don't want to double count those, so we subtract those off. 12 plus 6 is 18, minus 2 is 16, and there are 16 different numbers that are circled here. For our last situation, the first die larger than 4, again, were these 12 numbers that were at the bottom. The sum of 3 were these 2 numbers that were right here. And we're doing a probability question again. So we're going to do the probability of A plus the probability of B minus the probability of A and B. Same formula we used in the first example. The probability of event A are these 12 numbers that were circled in blue out of 36. The probability of B are these 2 numbers that were circled in red. And our intersection, well, they have nothing in common, so we don't have to subtract anything off. There are no duplicate items. All you have to do are count the events that are in blue and red. There are 14 out of 36 altogether. That is equal to, when you divide both top and bottom by 2, that's equal to 7 over 18. The last thing we're going to do is use a Venn diagram to answer probability questions. Here's a situation where numbers inside circle M are going to represent percent of people who are fans of the Mud Hens. Numbers within circle K are percent of people who are fans of the Knights. If you're inside this middle region, you like both teams. If you're not inside either circle, you don't like either team. We're going to use the Venn diagram at the right to find the following probabilities. And we're going to start with the probability of M, the probability that somebody likes the Mud Hens. So what we're working with is any number that's within this circle. Any number would include the 0.5 and the 0.1. They're both within this big circle. So we'd say the probability is equal to 0.6. The probability of M and K is basically anybody that's inside circle M and circle K. So you have to be inside this big, we'll call it this big blue circle right here, and you've got to be inside this big red circle, we'll say right here. Now who's inside both of these circles? Well, not the 0.5, they're not inside the red circle, not the 0.2, they're not inside the blue circle, this 0.1. So the region we're looking for is this region, kind of right in here, and we'll call that 0.1. The probability of M and K, we're still dealing with the same regions, but you can be inside circle M or K or both. It doesn't matter. So we're working with people inside all 3 regions. That's everything. You can be in circle A, circle B, or both circles. It's anybody inside here. And if you add these 3 probabilities, you get 0.8. Not circle M is anybody that's not inside circle M. We already kind of know where circle M is. Who's not inside circle M? Well, these people that are part of this circle K, as well as anybody that's not even inside the diagram itself. So that would include basically everybody kind of that's out here. Now we haven't talked about what's kind of out here yet. I'll include this area right here. So who's kind of in this region here? Well, what we're working with is everybody but the 0.5 and 0.1. So if you want to do 1 minus who's in circle M, which was 0.6, we've established that already, you get 0.4. It also helps us answer the last question, which is who's in neither circle M nor K. So you're neither M nor K. What this means is basically you're not in M and you're not in K. That's people in this outer ring right here. Now we know there's 0.5, 0.1, and 0.2 inside all the circles. That's sort of like this middle probability, 0.8. So whoever's left over is in this outer region, and that would be your 0.2. That's who's in here. And if you were to add all 4 of these probabilities, you'd get 1.